Yes, welcome. We should start with you introducing yourself and a little bit about what you're talking about, and maybe a little bit about your background and what you do.
So my name is Stefan Karpinski. I'm one of the creators of the Julia programming language, which is a new programming language for technical scientific computing. My background is mixed. I have studied mathematics, but I also did graduate work in computer science. And at some point, I got frustrated with the existing tools in the numerical space and shared my frustrations with one of my friends in grad school. Introduced me to another. His name is Viral Shah. He introduced me to Jeff Bezanson, and we decided to actually try to do something about it.
Right. So Julia is. It's kind of an interesting language because I don't think there are that many languages that are in the same space. My impression of the current languages for scientific computing is that mostly it's high-level languages mixed with very low-level C.
Yeah, so the classic combination is it's this two-language compromise where you say, okay, we're going to have a high-level language like MATLAB or R or Python. And then if you need, all of it is implemented in C. And then if you need to do something yourself that's really high performance, has a, performance critical, you write a C extension. Right. And we were really trying to have what Graydon Hoare described as a Goldilocks language, which is, he's putting it in the same category as some Lisp implementations. Dylan, it's a language that tries to say, look, it's not going to be perfect, but we think we can get something that is good enough for both high-level and low-level work, all in one language.
Right. A pretty pragmatic approach that way.
Yeah, so some of the interesting trade-offs are high-level languages have traditionally said things like, okay, well, we want integers to work mathematically, but we don't care about their performance that much. Right. Now, if you're going to bridge that gap between high level and low level, you can't really do that because all of your for loops are written with those integers.
Yeah.
And so if those integers are, 2-3 times slower than normal integer operations, then all of your codes sort of suddenly become slow. Yeah. So we have a high level language that uses machine arithmetic.
Right. So what does Julia do to achieve high performance? Because it's also not quite just high performance, since Julia is still garbage collected, if I understand things correctly.
Right. Well, so for a lot of workloads, garbage collection actually doesn't matter very much.
Right.
So, for example, if you're doing a lot of work with, let's say, all of your data is actually just unboxed data, floating point numbers or complex numbers or something like that inside of a huge array, then your object graph is kind of tiny. You just have a lot of data. And that's actually not an unrealistic work case for a lot of scientific computing problems. If you, for example, want to build a huge, pointer graph of some kind, which, people do in garbage collected languages like Java and C#, then the garbage collection becomes much more of an issue. Right. But we're sort of in a niche where it maybe doesn't matter as much. So we haven't, we certainly have to do work on our garbage collector, which is very simple and straightforward at this point, but it's actually not as much of a pain point as you might imagine.
Right. So Julia is very well rooted in that niche of scientific computing. Mm-hmm. But it seems to me, coming from the outside, that it could actually be very useful outside of that space as well.
Yeah, I think that's true. I think that we've tried very hard to keep it general purpose. There's absolutely no reason you can't use it. You can actually. There's a web stack built in Julia. You can do text processing. You can do anything you would do in any other language. You can also do. But it's good to have a focus initially. It's good to have a problem area that you really want to make sure that you can address excellently.
Yeah.
And the good thing about numerical computing is that it's full of challenges. We really have not solved this area, whereas I think there are parts of computing where we kind of have solved the problem. There are still problems like numerical computing, like concurrency, where new languages are really making strides and making things that previously couldn't be done much more reasonable.
So how does Julia handle things like concurrency? Is that something you're looking into, or is there
so there's the current situation is that you can you can do distributed computing. This is an interesting approach. We actually added support for distributed computing before threading.
Right.
And that was because we felt that it was more important to be able to tackle really big problems than to really maximize the usage of threads on a single machine. But now we're actually starting to look at multi-threading, and there's an experimental branch that has multi-threading support. It only works on Linux at this point, but we get pretty good scaling up to 80 cores or something like that. You get pretty good linear scaling,
right.
Which is non-trivial, but it's definitely not usable yet. The threads branch is very experimental, but it works.
But you're not looking into things like transactional memory or like alternative models?
No. So the concurrency model will actually be pretty similar to Go.
Right.
So Go routines are essentially coroutines which can actually execute concurrently.
Right. You have coroutines and you have channels that communicate.
Right, exactly. So we actually already have coroutines and channels.
Right.
We just don't have coroutines that actually execute concurrently. So that's basically the only change is that you have the exact same programming model, but now it will actually it might actually start working on a different thread.
Right. Well, that's a tricky problem actually, moving coroutines over to multiple threads, because you start getting all these interesting problems of I/O and shoveling things between threads and so on.
Yeah, I mean, one of the practical issues is to work out is how do you do I/O?
Yeah.
Do you have an I/O thread? Do you have a pool of I/O threads? Does each thread do its own I/O? We haven't really addressed that yet. So far, the threading work has all been on actually just doing the computation, not getting or putting data somewhere.
Right. So Julia is also based on the LLVM, if I'm correct.
Yeah, we use LLVM for code generation. LLVM is a phenomenal framework. It's one of those abstractions that's actually a pretty good abstraction. I think for the first 2-3 years, we hardly ever had to poke under the hood and do anything funny with it. You just you ask LLVM to generate code for you. It generates code. You run the code. Yeah. End of story. We've reached the point where we're pushing things where we have patches that need to go into LLVM that we upstream periodically.
Right, so that was going to be my question, because I've dabbled a little bit with writing languages on top of the LLVM API, and one problem is that LLVM develops quite quickly.
Yeah,
so
it does.
if you're working on like LLVM 3.4 and then you try to move to 3.5, quite a lot changes. So
yeah, I mean, so we handle that in the classic tradition of a ton of if-defs.
Right.
It's fortunately it's not exposed to the user at all. It's just you change LLVM versions and the if-defs change, select different code. One of the problems we have had is that distros don't seem to understand that LLVM versions aren't fungible. Right. So they'll insist, you have to use 3.4. We actually have, because there were some features in the old JIT, LLVM has changed JITs, and we were in the 3.4 version, the new JIT still wasn't usable for us, but the old version was also broken. Right. So we had to skip it, and there's distros who are insisting we use 3.4, and you're like, well, we can't. Ouch. It doesn't work. Yeah. So I hope that distros will package multiple versions of LLVM.
Yeah, it's unfortunate one of the big wins with LLVM is that it's written in C++ and it's like a nice API to work on, but at the same time, since it's written in C++, trying to use shared libraries, again, this looks like it's
it's very difficult. We've recently gotten the ability, which is pretty exciting, to call C++ code directly, which it's a little bit insane, but this is what you have to do essentially to call C++ libraries is to have a C++ compiler. Yeah. So what we do is we actually use libclang. We load libclang into a Julia process, which can then dynamically just generate the correct code to call C++ things on the fly. It even does template instantiation, which is a little bit, that's pretty nuts.
Yeah, that's pretty nuts.
Yeah. So it's very cool, really useful.
It's pretty cool that it actually works.
It is. It's it always makes me a little nervous, but then it works.
Don't start thinking about why it works.
Yeah, exactly.
So how much use outside of the community have you seen Julia? Are there any like games using Julia or other applications?
So this brings us back to garbage collection. For games, you do really need hard real-time constraints. You can't just pause for 200 milliseconds to do GC.
Yeah.
So we have not seen people using it for games, although there was a guy who wrote a really cool Quake engine in Julia. So it was a Quake 2 engine called Quake.jl. He was initially writing it in Go, and we were hanging out. This is a guy who was a hacker schooler. So I don't know if you know about the hacker school, sort of writers retreat for programmers. And he was encountering the problem that he really needed to do matrix multiplies, and Go didn't have good support for it at the time, which has probably changed by now. Yeah. But I was like, well, I don't want to peddle my own wares too much here, but we can do matrix multiplies really easily. Yeah. And he actually got really good performance out of that. And I don't think GC was a big problem.
Yeah. So I think, because I have a games background, so I naturally think in those terms. But for the GC, Julia seems great for games because you have all the matrix multiplication and vectorization.
So we do have an experimental generational incremental garbage collector in a pull request, but it's got a few outstanding issues. It's a little bit crashy. Not terribly, but you don't want to merge change the GC and have it make the language be crashy. So, but I think a lot of people are very excited about that. The generational part helps everybody because it means that you just spend less time doing GC. The incremental is really good for more real-time things because you can actually start doing GC, stop for a while, come back, and keep going.
Yeah. So it's very cool. Yeah. Let's see. So why did you need a new language? I guess I was kind of into that before, in the space, but it seems like we're kind of in a time of a lot of new languages, which is really great. But how come you guys felt that no, we really can't fix any of the existing things. We just need to do something new.
So the basic issue. So if you look at numerical computing languages, each of them takes a different approach to specializing for numbers. And that's why there's so many of them. There's a lot of different ways to think about specializing for numerical work. And the text processing world actually used to be like this, right? There was Snowball, Spitball, Icon, Commit, Perl 4 was essentially a text processing language. And that all just died and went away. And that's because we figured out how to make general purpose languages good enough at text processing that now you're well, why would I use Snowball? That doesn't really make any sense. Yeah. You just use Python. So I think that has yet to happen in numerical computing.
Right.
And it's happened if you have a language where numbers don't have to be special anymore, where numbers are just another user-defined data type. Right. So for example, there's a reason the reason the C99 standard includes a specification for complex numbers. Why does it need to have a specification for complex numbers? Why can't you just define a new type for complex numbers? Yeah. And the answer is that you can't really do it. You can't make complex numbers particularly usable with the features of the C language. So you have to bake it into the spec. So the question then becomes, okay, well, what do we need to do in a language to make it general enough that you can just go ahead and define a complex data type yourself and have it have all the properties you need to actually use it for real work? Yeah. And there's a bunch of different things. One of the features that Julia has that we added for this particular reason is immutable composite types. So you can define your complex number type, and it's immutable, which is what you want numbers to be, because you don't want to, 1 plus 2i is 1 plus 2i. Yeah. If you change it to 1 plus 3i, it's not the same number with different contents, it's a different number. Right. So having immutables is really helpful. It's also good for the compiler and for layout and memory. Multiple dispatch is for interactive use in a dynamic language. You really, really you want numeric operators to depend on the type of all of their arguments, not just one.
Right.
When you write 1 plus x, is that 1 dot plus of x? That's what it is in Ruby, and that won't work unless you monkey patch the number type. Yeah. In Python, there's this radd hack that lets you do it, but of course that only works for plus.
Yeah.
It falls apart for other things. So multiple dispatch is like a disciplined way to actually do that properly.
So I would love to go into that more, because I think that's one of the really interesting features of Julia. Mm-hmm. In Common Lisp and CLOS, you have multi-methods, which is roughly the same thing, where you have, I think a lot of people who are used to object-oriented languages and Java and so on, kind of get stuck on the idea that polymorphism always depends on the object, like the first argument. Yeah. But actually, you could argue that true polymorphism depends on all of the arguments. And that's closer to what you have in Julia.
I mean, it's clearly a generalization. The question is, how useful is that generalization? And we've found it to be remarkably useful, to the point where you've got to wonder why other languages haven't been doing this.
Right.
I think part of that is implementation complexity.
So I think one thing that fools people is that in Common Lisp and CLOS, the dispatch is runtime. So when you call the method, it actually looks up which method to call, which is very slow.
Right.
But in Julia, you do it at compile time.
Well, we don't always. Semantically, it's at runtime. So you can always think of everything as happening at runtime. But what we do is we very aggressively specialize code for the types of the arguments of the code. Right. So if you call a function with 3 arguments, an int, a float, and a string, you'll have a special version of that function for the int, float, and string argument types.
Right.
And then what happens is you recurse down into the code, doing type inference and code generation, and calling very specialized methods on all the functions that are in there.
Right. So at JIT time, you can kind of select the right function.
So JIT is crucial there, because you don't necessarily know what code you're going to need in advance.
Yeah.
The other thing is you're essentially trading off memory for performance, which is, this is not a new technique. We're not, this was done in high-performance implementations of Smalltalk, other related languages, implementations like Self. Pioneered a lot of this stuff. But at the time, machines were, relatively slow, and compilation, that JIT compilation took a noticeable amount of time, and you couldn't really afford that much memory.
Right.
Now we're in a totally different world, and in particular, we're in a world of, when you're talking about technical computing, nobody cares that you're generating 50 megabytes of code at runtime when you're working on a terabyte data set.
Yeah.
It just doesn't matter.
The situation really has changed that way over time. You couldn't have done it the same way 15 years ago.
Well, you could, and people did, but it wasn't an acceptable trade-off at the time.
It couldn't be widely used.
Yeah. Now, and we'd like to slim down our runtime, but it actually just doesn't matter that much.
How large is it now?
I think it's about 50 megabytes for the Julia runtime by itself. A lot of which is, we bundle a bunch of numerical libraries like basic linear algebra subsystem, BLAS. Fast Fourier transforms, arbitrary precision arithmetic, and those take up a bunch of memory. But it's scientists really want to have a complete solution out of the box where you just start it up and you can start doing work immediately.
Yeah, and why wouldn't you?
You might want to, for example, write programs for an embedded system, and that's a target area where we actually have gotten a fair amount of interest.
Right. So that was going to be like my next question is. Julia is still a very young language and still in development.
Yep.
I'm not sure, have you released 1.0? Or?
No, we haven't. We're in the release process between 0.3 and 0.4.
Right.
Which has actually been a fairly... 0.3 was a very conservative release. 0.4 has actually been fairly adventurous.
Right.
But we're getting really good at doing the deprecation process, so that what you take a piece of code that used to work and it'll still work, but you get a bunch of warnings that tell you very specifically, this has been renamed to this.
Oh, nice.
You need to change this to that. So if you just go through and fix all the warnings the first time, you've pretty much ported your code.
Well,
that's the way you want to do it.
Yeah, it's very nice. It's not quite as nice as Go's...
Right, Go has a tool that changes the
code.
code
Go has an automatic tool for rewriting the code. that's hard to do in a dynamic language.
Yeah.
It's not impossible, but it's hard.
I would be kind of scared to have it do that in my code. I mean,
Yeah.
really cool, but scary.
Yeah. I mean, you would basically have to drive it with some sort of trace execution.
Yeah.
Like you have to run some data through it, run some tests or something, and then figure it, automatically change the code. It's not that hard to just go through and fix all the warnings. So.
Yeah. So what kind of things do you want to add to the language at this point? Like what is on the roadmap?
So we already talked about threading.
Yeah.
Better garbage collection. Static compilation. So one of the things that we're in a position to do that's a little unusual for a dynamic language is because we have one of the nice things about multiple dispatch is it actually gives the compiler an amazing amount of good type information.
Right.
So because you define complicated behaviors by specifying what a function does on various combinations of types, you now know what the types inside of those method bodies are.
Right.
And there's different levels of static compilation. You can take a Julia script and turn it into a binary that links against LLVM and the Julia runtime, and that'll work. Right. And you can even still do JIT. That's, because you have LLVM.
Yeah.
The next thing you could do is you could actually get rid of LLVM, and then if you found yourself in a situation where normally you would JIT something, you just run a slow fallback.
Right, interpret at that point.
Right, and then what you just have to do is make sure that you've pre-compiled all the things you think you're going to need. You might end up in a slow case. The slow case is still faster than dynamic languages typically are.
Yeah.
So it's still going to be fast, no slower than like Python or Ruby, or certainly not slower than Ruby. Then the next lowest level, this is what I think would be really exciting, is to do completely static compilation.
Right.
Where you can just generate a binary that is standalone, has no dependencies on any dynamically loaded libraries, and you can just ship it on a server.
Right.
And as long as the architecture is correct, it'll run and do what you want it to do.
So would the idea there be that you would at compile time detect if this is going to have to be done at runtime, and you would stop compilation and warn or something along those lines, or?
Yeah. So essentially, what you do is when you're doing code generation, you generate code for the things you expect to need to run, and you generate code, generic slow fallback code for everything.
Right.
So, an interpreter is essentially just a completely generic slow implementation of code for an entire programming language.
Right.
So you can always just fall back on an interpreter.
Right. So in the static code, you would compile in a little interpreter for those cases.
Yes, exactly. The static code would have, except the interpreters would be basically a customized interpreter for each function, which means that some things are actually specialized. So it's a partially compiled interpreter. Right.
So you would still have like the instruction dispatch in the interpreter, but it would be a much smaller case set. Yeah.
Yeah. So
that sounds interesting.
Yeah, and there's a lot of people who would be really excited about having static compilation. That's I can't say exactly when that'll happen, but it's been in the works, and a lot of progress has already been made on it.
Yeah.
I'm currently working on an overhaul of our I/O and string subsystem, which is currently a bit of a dog. It's not terrible, but it's there's a lot of overhead because we use array objects to represent strings, and the array objects have, in dynamic languages typically have there's 60, 70 bytes of overhead.
Right.
Which means now, because a string uses an array, if you want to have a one-character string, it takes, some 70 bytes, which is outrageous.
Yeah.
And there's a lot of strings that are very short. That is common.
Yeah, so you have plans to improve that now?
Yeah, I have a branch that I'm working on that just reduces the overhead for short strings. They would actually be stored immediately with no, not even need to be heap allocated. They're just 2 word values that are passed around. So 128 bits on a 64-bit platform, or 64 on a 32.
So do you know of any larger projects using Julia at this point?
There's a number of academic projects that are using it. That's and those you kind of know about because they're academic, so they're pretty open about it. There's a number of labs at a lot of optimization work being done at MIT. There's a lot of numerical linear algebra work done at MIT. Stanford has got a lot of courses being taught in Julia now, and they're doing a lot of work on optimization as well.
Yeah.
So there's some companies. I can't talk about all of them, but there's some finance companies that are using Julia for things. The finance companies are, notoriously secretive about their technologies because it's a competitive advantage.
Yeah, but you can see the problem area is kind of overlapping.
You can see the potential.
Yeah, it makes a lot of sense. And then there's some applications in aerospace too, which are also somewhat secret.
Right.
I'm actually not sure if I can talk about those or not.
We didn't hear anything.
I shouldn't, since I don't know.
Drones.
Yeah.
Right. Oh, that's cool.
Yeah. I know some people at Facebook are interested in using Julia. Their main blocking issue is that they need the static compilation to work.
Right.
Which totally makes sense. So once that happens, you might start seeing that. And one of the nice things about that is that once you have static compilation, you can generate a library in Julia that is indistinguishable from C.
Right.
Nobody needs to know that it was written in Julia. They could just call it as though it was written in C.
Yeah, I mean, especially when you have the C++ interop, you can even call back to C++ and C. Too.
Oh, I've written a ton of code where you do layers where you pass, so you can take a Julia function and turn it into a C callable function with no overhead, because you actually tell it the signature you need, and then it compiles that version and gives you a C function pointer, which you can then pass to the function that expects a callback, and it doesn't know that it's not calling a C function, so you can get multiple layers of going back and forth between languages that way.
So have you seen anyone using it like SciPy, like still using Python or something like that, but using Julia instead of C?
So the Python interop story is really good. Steve Johnson, who's also the author of FFTW, wrote a PyCall package, which is just really, really cool. It uses that ability to interop with C, and the fact that Python has got a really, really good embedding story.
Yeah.
So when you're calling Python, you're basically just calling a really capable C library, essentially.
Yeah.
And so you can actually define a mutually recursive function that calls back and forth across the languages, and you got one stack frame of Python, one stack frame of Julia, one stack frame of Python, and so on.
Right.
Which is a little impractical. You don't really want to do that, but you can.
Yeah.
It works.
Yeah. So what is it like debugging Julia? Because it's kind of, debugging Python is quite nice because you get nice stack trace and so on, but debugging C can be painful.
Yeah. So the debugging story is about to get a lot better. There's a patch waiting to go into LLVM that gives us access to the ability to use GDB and LLDB like debugging in a Julia stack frame.
Right, so you could step Julia code.
Yeah, and so then you'll be able to we're not going to use LLDB ultimately, but you would be able to pop up LLDB or GDB and step by step through Julia code.
Right.
Stack traces are actually, they're pretty good, but they're problematic. In a language like Python, you can just sort of unwind your interpreter stack. And you have a stack that's a data structure that you created, so you know how to walk it. In a compiled language, even if it's JIT compiled, you now have to be able to recover what was going on from an actual stack frame, which is tricky. There's an ABI for that, but nobody respects it. It's weird. Like, it's supposed to be as easy as just walking a linked pointer list, and for some reason, to save 8 bytes per stack frame, everyone just doesn't do it. Which I would much rather. And there's even a flag to ask the compilers to do it, which they ignore. So this is why we can't have nice things. Well,
I guess maybe. So one of the issues, it's not really a big issue, but one of the issues that I had with LLVM is that it's really, really C compiler. Like that's what it is.
Yeah.
And there are some errors, like especially like GC and if you want to use different calling conventions from C, like you're just on your own. Like
yeah, you do. There's a chunk of code from Clang that you need to copy and paste into your code base to get the C calling convention to work correctly.
Yeah.
Which we were just harassing some LLVM people the other week about. Hey, how about just actually including that? Rust has included it. I think, Swift includes it. Well, we don't know because there's no source code open for Swift. But I am excited about Swift because it's a cool language. And also because it means that there's a commitment to a broader set of languages in LLVM. Because LLVM, Chris Latner is the creator of LLVM, also the creator of Swift. He's at Apple. I think he's the head of developer tools.
Yeah.
So now they also are committed to supporting languages that aren't C.
Yeah. Yeah, that's true. Swift is really good news for everyone using LLVM, I think.
And I think the FTL, the WebKit FTL,
yes,
is that also an Apple project?
Yeah, it's an Apple thing.
Right, so that's actually a dynamic language that's using LLVM JIT.
Oh,
so
that's a pretty big thing as well, yeah.
That means they now have skin in the game for LLVM supporting dynamic languages.
Right.
So that's also exciting.
Yeah.
And we're going to use some of the features that they improved some of the GC support. LLVM being able to actually understand what things in your stack are pointers to objects that you need to walk through when doing GC. Currently, we just have a shadow stack,
which is slower, but
it's slower, but it's simple and it works.
Yeah.
And it's better to have something that works than something that doesn't.
Yeah.
So.
Yeah, that's one of the things that's been frustrating me with LLVM because it's basically been like there's some kind of support for GC and for root finding in LLVM, but it's basically broken.
Yeah.
And then everyone uses shadow stacks and it kind of works, which means that nothing really happens. But it's great if the FTL stuff ends up
maybe in some new version of LLVM the GC, the stack support for GC will actually work.
Yeah.
Fingers crossed.
Yeah, exactly. Knock on wood. And then the other thing is they have support for dynamic stack frame deoptimization, where you take a code that's running optimized and does some values may not actually be stored in registers, they may not be stored on the stack at all, and you can rewrite that and map it to what the deoptimized code needs, and then switch to running deoptimized code. For example, when you're debugging.
Yeah.
So that's
nuts.
it's crazy stuff, and I'm really glad that someone else implemented it. And if we get to just use it for free, that's phenomenal.
Yeah.
But I'm not. I suspect that may be tricky to get working.
Yeah.
Could be.
We'll see.
Yeah, I mean that's one of the things you read about the stuff they're doing with the JavaScript VMs at Mozilla and so on, and for WebKit, and some of it's just like insane.
Yeah,
it's one of those things like
really crazy.
You might come up with like on paper and then go like, no, this is too complicated.
So almost all of these things I think came from the Self project.
Yeah.
So Self had almost all of this the aggressive method specialization, JIT stuff in general, the dynamic stack frame deoptimization. All of these crazy techniques were developed during that project.
So was Self an inspiration for Julia? Like, is that something you used at university?
No, only in the extent that I read a lot of research papers on it. I'm not actually a small talk programmer or a Self programmer or anything like that. But I mean, I remember in the early 2000s sort of discovering this trove of papers from that era and that research, sort of research area, and just like being super into it. Reading all of them, salivating over all these cool, crazy techniques.
Yeah.
I think we're actually relatively conservative about doing crazy things, though. We try to avoid, we try to keep it simple, because those are the things that are reliable.
So are there any things that you think you should, like any choices you shouldn't have made?
Should not have made?
Yeah, exactly. Like maybe that was not such a good idea.
Yeah, so the choices that we've had the most regret over, and it's not too late to change them, and we've actually have changed some and are planning on changing others, or at least considering it, have been for MATLAB compatibility. So initially we sort of felt like we needed to mirror more of what MATLAB did so that MATLAB users would be really comfortable switching languages.
Okay, so it's not like strictly binary compatibility.
No. You can't take a MATLAB program and run it with Julia or anything like that. Right. But you know, for example, the array concatenation syntax in MATLAB, you put square brackets around things and you can have arrays inside things. And people are always surprised because if you have what looks like it should be an array of arrays actually concatenates the arrays into a big array.
Oh yeah.
And that's, everybody looks at that and they're like, wait, what?
Yeah.
And except for the MATLAB programmers who are like, yeah, that's what it does. But it's, then you have weird things where you're like, well, what if I want to make an array of ranges or an array of arrays or an array of, and it would be much simpler if there was one syntax for making an array and one syntax for concatenating arrays.
I guess that's one of the things with Julia adding more strict types, like a better type system, whereas MATLAB is just, like it's an array or it's a matrix.
Well, in MATLAB, it started out that everything was just a complex matrix, and that was the only data type. And of course, if that's your only data type, it doesn't make sense to have an array of matrices because you don't even have.
Yeah, exactly. It's a nonsense question. Yeah.
So the only thing you could do is concatenate the arrays.
Yeah.
But we're clearly not in that world anymore, so it's probably a questionable choice. But we'll probably change it.
Well, that's very cool. Nice. I think I've asked everything.
I think we're about done.
All right, cool.
That's great. Thank you very much.
Yeah, thanks a lot for having me.
Let me put it this way, Mr. Raymer. The 9000 series is the most reliable computer ever made. No 9000 computer has ever made a mistake or distorted information. We are all, by any practical definition of the words, foolproof and incapable of error.